everyone. I'm coming on now to talk to you about dot product. And what I love about engineering is finally understanding the reasons for learning some of the math and the science that you learn in the previous classes. I remember learning about how to do a dot product in calculus at some point, but I never really understood the reason for learning it. And I want to show you that in statics, what it actually means. Maybe some of you had math teachers who actually explained the purpose of it, and that would be awesome. But in any event, let's just go back and figure out what dot product is. So let's say we have vector A and we have vector B. And if we wanted to dot vector A and vector B, there were two different ways. One way is by taking the magnitude of vector A, multiplying it by the magnitude of vector B, and multiplying it by the cosine of the angle between those two vectors. And what does this give you? It gives you a scalar value. The solution is scalar. It has no direction. Another way to solve for a dot product is if you know the components of the force, you take the x component and multiply it by the b component and add to it the x component of y and b component of y, and then z component of a, and oh boy, yeah, and the z component of b. So I took the x, y, and z component of A and the x, y, and z component of B and multiplied the x's together, the y's, and the z's together. And again, you come up with a scalar. And what's interesting here, if you could get the same value, whether you do it this way or this way, let's say you have a situation where you know what AX is, what BX is, AY, BY, AX, and BY. Let's say you know all those, which means, let's say you know what the vectors are, vector notation for A and B. Can you find the magnitude of A? So what I'm saying is, if you know AXI plus AYI plus AZK, and you know the B vector is BXI plus BYJ plus BZK. If you know these, can you find the magnitude of A? Sure, we already know that by doing our checks. From this, we could find out what the magnitude of A is, because the magnitude of A is AX squared plus AY squared plus AZ squared, all under the radical. And from this, we also could find out what the magnitude of B is, which is BX squared plus BY squared plus BZ squared under the radical. So if we know the components of both vectors and we know the magnitude of both vectors, couldn't we solve for the angle between? Sure, because we know that AX times BX dotted with BX is equal to AX BX plus AY BY plus AZ BZ, which equals the magnitude of A times the magnitude of B times the cosine of the angle between A and B. So I certainly can solve for that. The cosine of the angle, actually, let's say this. Angle AB is going to be equal to the inverse cosine of AX BX plus AY BY plus AZ BZ over the magnitude of A, magnitude of B. Right? Everybody's good with that? Okay. So we already know this math part. Now the question is, well, what does it all mean? At some point, when we were finding components of forces and it was a problem where they were giving you an angle, for instance, and you had some force here that had an angle of 15 degrees, if I wanted to find the Fx, the x component of the force, I know it's the F component times cosine of 15 degrees, because this is our direction angle. It is the angle between the force in question and the positive x-axis. This looks similar in that we're using components, we're using forces, and we're using a cosine angle. In a way, this is doing the dot product. And the reason why is because what you're doing is you're really dotting two vectors. You're dotting, and this represents unit vector. You are dotting this vector with the unit vector in the x direction. And we know that when we dot two vectors, it's the magnitude of f times the magnitude of the second vector times the angle, the cosine of the angle between, which is the direction angle. And what is a unit vector? What is the magnitude of a unit vector? It's 1. So in the end, when you dot f with ex, it's equal to f times the cosine of theta x. So this really, and we know that f dotted with the unit vector is really equal to the x component. Let me just make this a little bit smaller here. This right here is the unit vector. And in the end, when I dot the force vector with the unit vector, I wind up getting fx, the x component. So when you dot a force vector with a unit vector, you get the component of the force in the direction of the unit vector. Okay, I'm going to stop.